Our final derivation will be for a toroid, which is a solenoid that is twisted into a circular shape. This shows it from the side. You can see the circles around the outside and the inside of the cross sections of the wires so that the current is coming out of the page towards us on the outside and into the page away from us on the inside of the loops. So we've picked our Amperian loop to run around the ring down the middle of the coils. And you can see that this is in the same direction as the magnetic field that is uniform inside the coils. So let's work through this now on the tablet. So again, this shows a cross-section of our toroid, and what we have is wires you can see coming towards you along the outside of the toroid, and then you can see the wires on the inside with current going away from you. So the magnetic field will be going in a circle around the loop, just like in a solenoid. Remember, the magnetic field runs down through the coil. Here the coil has been turned into a circle, so the magnetic field goes in a circle, and we take our Amperian loop in that same direction as the field, so around the circle. And so all the points on the loop are a distance r away from the center. So we have our equation that B times ds is mu naught times the enclosed current. So B, since it's a constant around there, times ds around a circle, which is 2 pi r, equals mu naught times the current in one wire times n, where n is the total number of turns. So we have B equals mu naught I over 2 pi r times n. So that's for the magnitude, the direction you get from the right-hand rule. Now we can actually prove that if we took a loop outside, that the magnetic field outside would be 0, because for every bit of current coming out of the screen around here, the same amount of current is going into the screen here. So for any loop outside the toroid, the net current inside is 0, and so there'll be no magnetic field once you are outside the currents along the outside of the toroid.